This presentation introduces a proposal for Working Group 27 on North Pacific climate variability and change. I'm Emmanuel Di Lorenzo, and I have other two contributors to this presentation, Dr. Shushiro Minobi and Dr. Mike Foreman. A little bit of background and motivation on this working group. The essential goal here is to develop essential understandings of the mechanisms of North Pacific climate variability and change that can better guide the formulation of process-based hypotheses underlying the links between ecosystem dynamics and physical climate. Now, I'd like to give you some background on the concept behind this working group. This map shows the sea surface temperature anomalies during the positive phase of the Pacific Decadal Oscillation, or PDO. The PDO is a climate pattern or mode of climate variability that has been often used to characterize both the physical and biological state of the North Pacific. In fact, this has been very useful to link, for example, changes in sea surface temperatures with biological indicators in marine ecosystems. Now, although the PDO has been very useful, we know that in the Pacific there are many more modes of climate variability that are important in characterizing the physical and possibly also the biological state. So, for example, there's a group of atmospheric modes, oceanic modes, and also coupled ocean-atmospheric modes. The Pacific Decadal Oscillation is an example of an ocean mode, like El Niño Southern Oscillation is an example of a coupled ocean-atmospheric modes. In recent years, it has become apparent that other modes of climate variability of the Pacific are also important. For example, in the class of ocean modes, the North Pacific Gyro Oscillation has emerged as an important mode of both physical and biological variability. Now, in the tropics, and together with the El Niño Southern Oscillation, it has been recognized that sometimes the El Niño may have a different type of flavor, also referred to as the Central Pacific Warming Pattern, and that this type of, let's call non-canonical ENSO, has important implications for the Pacific climate. In terms of atmospheric modes, we know that there's a mode of variability associated, for example, with changes in the Aleutian Low, but we also know from historical studies that there are other modes like the North Pacific Oscillation, which is perhaps less known to the ecosystem community, that is also important in characterizing the state of the Pacific. Now, given that we have this zoo, if you like, of different types of climate modes of the Pacific, the question emerges as to how are these modes useful to understand, quantify, and predict ecosystem variability. Now, it is often the case that ecosystem studies conduct simple correlation analysis between one or two of these climate modes and ecosystem changes as a way to establish a link between changes in the physics and changes in the biology. Although this has been an important approach to show that some of these modes, like for example the PDO and other biological variability, are actually linked, this approach ignores the process dynamics that link the physics and biology. And by that I mean that behind the correlation between changes in physics and biology, there are specific processes that establish that correlation, and we need to seek a better understanding of what those processes are. Now, the fact that often we don't understand these processes may stem by the fact that there's confusion about the physical processes and dynamics underlying these climate modes. So the first term of reference of our working group is to try to summarize the current understanding of mechanisms of Pacific climate variability and change in a way that it becomes more readily available for scientists that do interdisciplinary studies, for example, the ones that try to link ecosystem dynamics and physical climate change. Now, we also know that over these last years there's been a lot of progress in the climate sciences in terms of understanding the mechanisms of these modes and also linking these modes together. In fact, it turns out that a lot of these climate modes are not just independent of each other, but they are tightly connected. And so here in this diagram, what I'm showing you is some of these recent studies, and some of them a little bit older, that shows the links and connections among these different modes, and each of these arrows indicates specific dynamics of forcing and response associated with these modes. So, given that we have this type of connection between the modes, then our working group will also try to evaluate the strength of the underlying hypotheses about these connections and dynamics with supporting evidence. Now, if we look at a diagram like the one shown in this picture, one could refer to this as a conceptual framework of Pacific climate variability. And I refer to this conceptual because these links are, conceptual in nature, and they have to, be better quantified and understood. Now, these type of conceptual framework can serve as guidance to ecosystem scientists to better isolate and understand the essential physical processes that are relevant to specific ecosystem dynamics that are being studied. Now, conceptual framework like these can also be synthesized in mathematical low-order process models of the climate. And by low-order process models, I'm referring to models that reduce the complex processes or the complex dynamics of the climate system to their basic elements and dynamics. So our second term of reference then is to develop these conceptual models or low-order models of North Pacific climate variability and change, which can be used by the climate researchers to investigate the mechanisms of climate variations and by the ecosystem scientists to explore hypotheses linking ecosystem dynamics to physical climate. And as we explore these hypotheses of the link between physical climate and ecosystem dynamics, we can develop process-based models of the connections between the two. So I would like to provide an example of developing a process-based model to link ecosystem changes to physical climate. So what I'm showing here is a time series of zooplankton in the California Current, and this is a time series, historical time series from the 1950 to present that was provided by Mark Homan at the Scripps Institution of Oceanography. Now if we look at a time series like this and we take the approach of connecting to this time series to a climate mode, for example the Pacific Decadal Oscillation, we can begin by using a very simple approach, that is to correlate the climate index with the biological time series. If we do that, here is plotted now in red this climate index, in this case the PDO, and for this particular comparison we see that the correlation is 0.41. It turns to be that this correlation is significant from a statistical point of view. But if we look more carefully at the two time series, we realize that the climate index has a lot more high-frequency variability, or more noise if you like, when compared to the smoothness of the biological index. One could potentially say perhaps we need to smooth the PDO index, in this case the climate index, to make the comparison look better. If we did that and we find the optimal smoothing for the climate index, for example by low passing the PDO index, we can actually achieve higher correlation of 0.55, and that's kind of the highest correlation that you achieve between these two time series by just smoothing the time series. Now the question of our working group is, can we do better than this? Another approach would be to develop a process model. In this process model we could recognize that the Pacific Decadal Oscillation is also an index of changes in horizontal transport, or changes in the currents that advect water masses in the ocean. Now these changes in transport have an important effect on zooplankton, in that the changes in the currents can displace the species in zooplankton along the coast, for example. If we write down this type of dynamic in a simple process model where the PDO is driving or forcing changes in the zooplankton, and if we also include some simple internal zooplankton dynamics, for example the length of the life cycle of this particular species, and we develop a simple process model and we compare the time series that comes from the process model with the actual biological index, we find here that the correlation is much higher. It's 0.84. The other interesting aspect of this process model result is the fact that the time series is also smooth in the same way as this zooplankton time series. And the smoothness of this time series is not an arbitrary choice. For example, we didn't choose to smooth the PDO index per se, but the smoothness comes from the process itself. So this process model itself includes the dynamics that smooth this time series. So this is a very powerful approach because it allows us then to really hypothesize certain types of processes and test them with these simple analysis to isolate possible mechanisms of connection between the physical climate and the ecosystem. Of course, building these type of process models is not always easy. In fact, it can be very complex sometimes to isolate what pieces of the puzzle are really important. So the third term of reference of our working group is to work in conjunction with ecosystem scientists to coordinate the development and implementation of process-based models, which include important processes in simple forms to hindcast the variability of available long-term biological time series. Together with this third term of reference, we also have an additional term of reference, which is to develop methods to identify and provide uncertainty estimates of decadal variability in recent historical climate and ecosystem time series. Now, there's another advantage of building conceptual frameworks and low-order models of the Pacific climate variability and change. And this advantage stems from the fact that these type of frameworks could provide improved metrics to test the mechanisms of climate variability and change in the IPCC class models. And in fact, this is our fifth term of reference, is to provide such improved metrics and to work in coordination with other PICES working groups and the future advisory panels to assist in evaluating those models and providing regional climate forecasts over the North Pacific. Now, this particular aspect of this of the working group 20 of this working group term of reference is that it provides also some continuity with the activities that have been that are being completed by working group 20 on the evaluation of climate change projections. Now, working group 20 is scheduled to end at the end of 2011, and therefore this new working group picks up some of the activities of the working group 20 in terms of providing these metrics to test the dynamics of these IPCC models. Our sixth terms of reference is to understand and fill the gaps between what physical models can currently produce and what ecosystem scientists suggest are the important physical forcing factors required for predicting species and ecosystem responses to climate variability and change. And finally, the last three terms of reference deal with trying to make our activities known to the rest of the world, and in particular 7, to maintain linkages with and to summarize the results from national and international programs and projects such as CLIVER, IMBER, and CAMEO, and so forth. And 8, to convene workshops and sessions to evaluate and compare results and maintain an awareness of state-of-the-art advances outside the PICES community, and to publish a final report summarizing the results. So to summarize, the goals of this proposed working group are to develop essential understandings of the mechanisms of North Pacific climate variability and change that can better guide the formulation of process-based hypotheses underlying the links between ecosystem dynamics and physical climate. The proposed chairs for this working group are myself, Dr. Shoshiro Minobi from Japan, and Dr. Mike Foreman from Canada. We also have a potential list of members for this working group, and here are listed, divided by the different countries that are part of PICES. And some of, actually 50% of the people listed here have already given us some informal notice that they would be interested in participating in these activities. Okay, this is all I have to say. Thank you.